Okay, welcome to the Object-Oriented Lecture, Part 2. So this time we're ready to look at some code to see actual implementation of what we drew out in the last lecture. So here we have abstract class shape. Notice keyword abstract in front of class. It inherits from both drawable and printable. So shape is a drawable, shape is a printable. Now look at the abstract methods here, also with the keywords abstract in front of them. Here, very similar to the interface. Let's review what the interface, let's say printable, looked like. Here, interface printable. Now notice there we have a method header with no implementation. It's an abstract class too, or an abstract idea too. But an interface is more abstract than an abstract class. It has no methods that have any type of implementation. An abstract class is one step down below that. It's kind of in between a concrete class meaning all methods are implemented, and an abstract class like an interface where there's no implementation whatsoever. It's just the logical notions. So back to shape. We have shape inherit is a drawable, is a printable, and we have still abstract draw methods and print methods. So we're not ready to implement these methods, but the compiler makes us acknowledge that by implementing the method headers as abstract methods. So therefore, it needs the keyword abstract. In an interface, it's not necessary for the keyword abstract because everything is abstract inside of an interface, whereas some things are actually concrete methods inside an abstract class. So we don't know how to draw or print yet, but we know that we want shapes that can both draw and print. The other thing we don't know here on this level here is area. So this may really help you understand the idea of an abstraction. We know that geometric shapes have a concept known as area. But if you just say, I have a geometric shape, there's no formula for that yet because you don't know what the shape is. It's just, let's say, a closed area. Now we have this is a concrete implementation, and I kind of cooked it up a little bit. Print area. So here we have a concrete method. And all it does is console write line, I am a base.toString shape, but I do not know the area. Okay, so this syntax here, the base keyword is the base object of this class. So since we don't inherit from anything else, C# compiler makes us inherit from object. So base is a reference, it's a keyword to say access to the direct ancestor of this class. In this case, object. So it's going to call objects toString method, which of course we've seen that. What it does, it prints the name. It'll produce, it doesn't print, it produces a string with the name of the class inside of it. I am a shape, but I do not know the area. So here we have an actual concrete method in the area where we also have three abstractions, draw, print, and area itself. So now let's take a look at our circle class. So circle is a shape. So we know the shape is a drawable and a printable. So circle inherits from those as well down the hierarchy. So we know how to calculate the circle area. So the abstract method can become concrete. So it's not a general shape anymore, it's a circle. So we can write a concrete method, in this case a property, to get and return the area of a circle. So this is actually an abstract property that we've implemented. We also know how to draw a circle, so we've implemented an abstract method, and we also know how to print a circle, again, the implementation of a previously abstract method, and also the print area method that the abstract base class shape declared, we now implemented. Notice public, new, void, print area. We'll come back and discuss the keyword new in a little bit. I am a circle with area here, so it knows how to behave as a circle. This is the property of radius, and that illustrates encapsulation. So we have all aspects of object-oriented programming in place here. We'll see polymorphism in a moment when we get to the actual program that exercises this. Okay, here. So we have circle. So we've declared generally, and we instantiate specifically. So remember, shape cannot be on the, we can never have shape on the right-hand side of a new, because shape is abstract and it can never become an object. We create a circle with radius 2 here. This is using the property initializer list syntax, so we don't have to write a constructor with radius as a parameter. We can simply use the public property here to set that up for the first time. We write on a circle, and here's our polymorphic behavior. So we declared generally shape, and we know that a shape's area is unknown. That is, we know that a shape has an area. It's an abstract notion, though. But because this is circle, it'll actually call circle's area calculation and do the area of a circle. Polymorphic question mark. We'll see if this is polymorphic or not. And this is also polymorphic. Do print. In this case, it'll print the shapes, the circle's do print method here. It's printable, but we're passing it a circle, and it will behave as a circle to print it. Okay, and here we have it running. So we have the circle, and its area is calculated. I am a shape 2 circle shape, but I do not know the area, and we print a circle. So we actually have 2 examples of polymorphism here, and 1 example that's not polymorphic. Here's the area of a circle. Here it knows how to print a circle, but this method here, the method print a circle, is not behaving polymorphically. That's why I put a question mark here. It's not behaving polymorphically. It's behaving like the implementation that we inherited from shape. Here, print area. Okay, and then we have circle here, where we've overridden it, but it's not saying print a circle. It's saying again, calling the base class method base.toString here. I am a shape2.circle shape, but I do not know the area. So I'm going to pause the recording right now and make this print area behave polymorphically, and we'll see what is necessary. Okay, I've made the modifications, and let's see what they are. So I need to use the keyword virtual in the base class method for polymorphic behavior to be set up by the compiler. So if it's not a virtual method, polymorphic behavior will not be in play in C#. So I made the similar change in Rectangle as well. I've overriding the print area. Let's look at Circle too. So instead of the keyword new, I now use the keyword override. So new in this context, the new in this context indicates we are hiding an inherited method, and override means we are overriding a virtual method. Let's look at the program itself then, and we'll see this comment here. So polymorphic question mark, it is polymorphic now because I've made those changes. The C# language wants polymorphic methods to be declared as virtual. Otherwise, the method call is hardwired at compile time. So unless the base class method says it's virtual, the method is actually hardwired. So this says shape, and then print area was hardwired at compile time to be shape's print area. Remember, it has an implementation as well. So without virtual, the compiler will hardwire this call into place. Now, the reason why it does that is because polymorphic methods are slightly slower than hardwired methods. Hardwired means the compiler at compile time resolves the address of the method and hardwires it into the code, whereas polymorphic methods have to use what's called a vtable to look up the polymorphic method and decide which is the correct method to call. It's fast, but it's slightly slower than hardwiring the address of the method at compile time. That's why they did it. This is not a concern in Java, so I know that the other language that you all will be studying at Grand Canyon University is Java. All methods are virtual in Java, so there's not this distinction with the virtual keyword. Okay, so now when we run it, we can see that we actually, instead of calling shapes print area method, we're now calling circles print area method. So it's polymorphic as well, joining area, which was polymorphic to begin with. And now this is polymorphic, the print area, and then print a circle also behaved polymorphic last time. And we can see that rectangle has been modified as well to behave polymorphically. Virtual in the base class, and then override in the derived class, and then you get methods that behave polymorphically. So, for example, we didn't have to do that to toString or think about it because object is written by Microsoft 20 years ago, and they declared toString to be virtual at that time, making it behave polymorphically right out of the box. When your own classes and your own class design, you have to keep in mind that you have to declare virtual methods in order to get polymorphic behavior all the way down the line. So that concludes our example. We've gone over encapsulation. We've gone over inheritance. We now know what polymorphism is, declaring generally but behaving specifically, many forms. And we know what abstraction is, the ability to express a logical notion without writing implementation until we get more specifically down the inheritance hierarchy.